Hey guys, so today is the last lecture, official lecture of the semester. This is the last topic we're going to cover is confidence intervals. There will be one more video posted reviewing the quiz and homework from this week, and then all of next week's material is optional because it's beyond the scope of the course, although I think it will be helpful to a lot of your projects, and I think it's useful information, so I wanted to cover it anyway. Next week we'll be going over regression, starting with simple linear regression and moving on to multivariate regression. So please use the time between now and the end of next week to work on your projects. They are due at the end of next week, and many of you have reached out to set up meetings to review your progress thus far and make sure you're on the right track. I hope more of you do that. It is the biggest chunk of your grade. And without any further ado, the last content we'll cover for this semester is confidence intervals. So we're going to start out, as usual, going over definitions. First of estimators, then of confidence intervals, and then we have a couple practice problems for you. Before diving into those practice problems, one for the population mean, one for a proportion, we're going to go over what critical values are and how they relate to confidence intervals with using the example from last lecture, the blackjack example. So let's start with a little refresher on statistics and what it means. The general idea is you collect a smaller amount of data, which we refer to as the sample, to make inference on a larger population, right? And this principle is going to be really important as we talk about confidence intervals. So first, let's talk about estimators. These are statistics that, true to the image that we just looked at, are about estimating a true population parameter using the sample. So you might hear people refer to it as a sample statistic or an estimator. The idea is you're taking an educated guess, so to speak, at the population parameter using your sample data. So we've used quite a few estimators recently. I want you to take a minute and think about which estimators we've talked about and what population parameters we're estimating when we use those statistics. So here's a few of the more common estimators we've been using. X-bar is often used to estimate the population parameter mu. Both of them are means. One's the mean within your sample, the other is the true population mean, which you very rarely know, which is why you estimate it with X-bar. The other estimator we use, and these are really kind of redundant, is the standard deviation within your sample versus the standard deviation within your population. And we saw how the formula for these actually vary very slightly in the denominator. And then I also included variance, which is nothing but the standard deviation squared. So those are some examples of estimators, and I think that background is going to be helpful as we discuss confidence intervals. So the idea behind a confidence interval is beyond just providing an estimator, and this goes back to the guiding principle from the very first day of class, you want to supply some measure of uncertainty associated with that estimator. And more specifically, when we use confidence intervals, we want some level of confidence associated with that measure of uncertainty. So you've probably seen and heard of 95% confidence intervals are the most common, and we'll get into that in the next slide. But that just means that we're 95% confident that this interval contains the true mean, and I'm actually not a huge fan of that interpretation. We're going to cover another interpretation in a future slide, but I just want to introduce this idea of a confidence level associated with your interval, because you want your interval to be unreasonably wide or unreasonably narrow, and the confidence level sort of helps you set the width of the interval. So generally speaking, all you do is you take your estimator and add and subtract a margin of error. So how do you calculate that margin of error? Well, it's your distribution's critical value, which we're going to talk about, like in that first example, multiplied by your standard error. And this is a specific example of a type of confidence interval for X bar. The assumption here is that X bar is normally distributed, which is why we're using the Z star to represent the distribution's critical value, because if we assume X bar is normally distributed, the Z statistic, the Z distribution would be appropriate, and then we find the critical value, which we'll go into more detail in a future slide, but it's the value at which you're covering 95% or your associated confidence level within that distribution. And then your standard error, you probably remember from before, is a little different than standard deviation. So you have your standard deviation like before, but in the case of X bar, right, it's over the square root of n. So you could also think about this as the square root of the variance over n, or you could write it in this format. You'll get the same answer either way. And instead of writing it as your estimator plus or minus some margin of error, you could also write it in parentheses where you state the lower bound and then the upper bound. And I want you to take a minute to think about why we might use these sort of standard parentheses as opposed to the square brackets when we write the confidence interval. And for those of you more familiar with math, you'll know that these parentheses are inclusive, whereas the square brackets are exclusive. And all that means is here I'm including the lower bound within the interval and the upper bound within the interval, whereas if I use the square brackets, it's up to the lower bound but not including it. So like 0.000001 away from it would be included, but the lower bound itself would not be if these were square parentheses. So that's the reason we use these parentheses. It's just a mathematical notation to be familiar with. So let's talk about how you interpret these confidence intervals. We talked about the formulas. Most generally is just your estimate plus or minus your margin of error, which is computed as your distribution's critical value, which we'll go over in more detail soon, multiplied by the standard error of that estimator. But let's talk a little bit about the confidence, how you interpret these confidence intervals. So as I mentioned before, the idea that we're 95% sure that the true population parameter lies within this interval, it's not wrong to say that, but it is a little bit silly because it can lead to interpretations that are more silly. So like, for example, you'll often hear people say things like, there's a 95% chance that the population parameter is in your interval. That doesn't really make sense though, right? The population parameter is either in your interval or it isn't. So let's talk about a way to say what they're trying to get at in a more specific way would be if you repeat the entire statistical process over and over again, meaning you collect your data, you calculate your statistics, you do the math to build your confidence interval. If you do that repeatedly, 95% of the time, 95% of your intervals will contain the true population parameter. That's a more succinct and accurate way to explain the confidence level. Whereas, there's a 95% chance it's in the interval doesn't really make sense, because as I said before, it's either in the interval or it isn't. So I definitely want you to use this interpretation when you're talking about your confidence interval. You might have heard me say, or you might remember from the previous slide, I said something to like, we're 95% confident it's in there. That's a somewhat true statement, but it's much harder to interpret, and it's kind of left up to the audience how they interpret that. So I think to be explicit, you should explain it in this fashion, that if you repeat this process over and over again, 95% of your intervals will contain the parameter. This interval may or may not, we don't know, but it was constructed through this process where we expect 95% of them to contain the true parameter. Or I just was more general and said X% because you can build a confidence interval for any level. Why do you think we use 95% most commonly? And I give you a big hint here as to why that's the case. So you probably remember from when we were conducting hypothesis testing that an alpha of 0.05 is the standard for no particularly good reason. Same idea here. An alpha of 0.05 corresponds to a confidence level of 95%, and we carry that over, that type 1 error over in our confidence interval calculations. You could construct 97, 99, 90% confidence intervals as well, but this is the standard for no particularly good reason, just like with our type 1 error / alpha. So let's go back to calculating these critical values, for example. We talked about our estimators. We know how to get those. In this example, it's X bar. We know how to get our standard error. That's associated with our estimator. So let's talk a little bit about how we come up with these distribution critical values. And I'm going to use the blackjack example to do that, even though you would not make a confidence interval for an ANOVA test. This is just, again, to iterate how you find these critical values. So to refresh from the blackjack example, we calculated this chi-square statistic. And we did that by following the formula expected minus observed squared over expected, right? And the order doesn't matter because you're squaring it. You could also say it as observed minus expected squared over expected. And we did that, and we got this chi-square statistic of 2.833, which corresponded to a p-value of roughly 0.14 or something, which did not duck our alpha of 0.05, and we concluded there was no difference. But what would have? So the question I have is, what chi-squared value would have ducked our alpha of 0.05? In other words, if we look at the chi-square distribution, where is there 5% or more data? Where is 5% or more of the distribution, 5% or less of the distribution to the right of this chi-squared value? And you can see in this graphic, it's at 16.9. That's actually not correct because you'll remember that the chi-square distribution depends on your degrees of freedom. It varies based on your degrees of freedom. In our example, there was only 1 degree of freedom because we calculated it as the quantity rows minus 1 times the quantity columns minus 1. And to bounce back to our example, there's 2 rows and 2 columns. We obviously don't count the totals. So we get 1 degree of freedom. However, I did like this image, even though the x-axis is labeled incorrectly, because this is kind of summarizing where that critical chi-squared value is. And here they're marking it as 16.9, but to actually find the critical chi-squared value, which I'm denoting with an asterisk, you just supply the area to the right of the tail, the degrees of freedom, and whether you want the lower or upper version of the tail. And I actually am realizing now there's a typo here. I did 0.025. This is a one-sided test, so I should have done 0.05. So it gave me a chi-squared value of 5. It's actually going to be much lower. Let's just do it real quick, just so we could see the true value. And all statistical software will do this for you. It's just essentially the inverse of calculating the probability associated with your statistic. In this case, you're supplying the probability and getting the statistic. And luckily, it remembered my code from when I ran this earlier. And let's just see what it corresponds to. So it looks like the critical chi-squared value is 3.84. That's what it should be. So I'm just going to update that, 3.84. And so what that's telling you is that in order to reject the null, you need to achieve a chi-square statistic greater than or equal to 3.84. And I use the about symbols here because I'm rounding and I want to be clear that these are not exact values. The decimals go on a little longer. And we observed 2.83, which is not quite there yet. So we already talked a little bit about why the image is contradictory, because it depends on the degrees of freedom, and we're using 1 degree of freedom, whereas this image I found off the internet, it's obviously using a different degrees of freedom. It looks like it's using something around 12, and the way I'm estimating that is because we know the degrees of freedom for a chi-squared is equal to its mean, and that looks to be roughly 12 because I know it's skewed to the right. So that's how you find the critical value for hypothesis testing. Now let's get into an example where we find the critical value for a confidence interval, which is going to be a little bit different because it's not going to be one-sided, it's going to be two-sided. And so instead of 0.05, we will use the 0.025. So here's a practice problem. It's the background is we're estimating how much time college students watch TV. We've collected a sample. This is our sample size. This is going to be important in calculating our standard error. And we've done some EDA, which is important because it helps to sanity check your results. We see that the mean is 2.09 hours per day, roughly 2 hours a day, and the standard deviation is 1.4. And I like that they also included some measure of spread, not just because we need it to estimate our confidence interval, but it's going to be important for sanity check because you can apply the empirical rule here, knowing that means are normally distributed according to the central limit theorem if your sample size is high enough. The other thing I want to point out is that this sample size is far and above the rule of thumb for the central limit theorem to hold at 1075, and that's going to come into play when we calculate our critical value. So let's go ahead and dive into this problem. Again, we'll use the standard 95% confidence interval. So this is our general formula. I want you to take a minute and think what you would use as the point estimator and what you would use as the standard error in calculating this confidence interval. And I'll flip it back to the information we got from EDA and about sampling to help you come up with those values. So probably the most obvious is our point estimator, right? We know that we're estimating a population mean according to the research question. We want to know the average time college students spend watching TV. We have the sample mean, 2.09. That's our point estimator. However, we want to include the uncertainty around it. What is our standard error? Well, it's just our standard deviation, 1.423, divided by the square root of the sample size, 1075. Why is it not just the standard deviation? Because we're not estimating a single point, right? We're estimating a mean. So the standard error associated with the mean is the standard deviation, but then you have to divide by the square root of n. So here is our formula, right? We're using 2.09, which we identified as our mean, and we're using the standard deviation of 1.423, and then we're dividing by the square root of the sample size. So we have all of that filled in. We have our standard error filled in, we have our point estimator filled in. The only piece remaining is the distribution's critical value. Now I put a t here for the t distribution. Why did I put in t as opposed to z or chi-squared or any of the other distributions we covered, f? Why do you think I put in the t? And the reason I put in the t distribution, at least to start, is because we don't know our true standard deviation, right? This is the standard deviation of our sample in our EDA. We don't know the population standard deviation, which is necessary to assume normality. So instead, when we don't know the true standard deviation, we use our t distribution. And our critical value for the t distribution, what do we need to find it? Well, remember there's many t distributions and they all depend on the degrees of freedom. So we need to know the degrees of freedom. For this scenario, the degrees of freedom is just 1 minus the sample size. We have the sample size here. Or actually, this is a typo, I think. Let me check real quick. Yeah, that's a typo because It's 1075 is the sample size, is what this should be, 1075. However, our degrees of freedom is 1 minus that, 1074. So that would be our degrees of freedom, 1074. And I'm going to estimate this with the normal, and I want you to think, or the z distribution, and I want you to think why I'm using the z distribution when I just told you in this slide that we need to use the t when we don't know the true standard deviation. So we're going to estimate this with the normal instead. Why? Given that we don't know the population standard deviation. And the reason we can get away with using the z distribution here is you might remember the cutoff point at which the t distribution is equivalent to the z distribution is at about 30 degrees of freedom, right? They're not exactly the same. The t distribution has slightly higher tails, but as your degrees of freedom goes up and up, and your sample size, right? Because degrees of freedom is nothing but sample size minus 1. So as those two things increase, you get closer and closer to a normal. We're at 1075 for our sample size, which corresponds to 1074 degrees of freedom. That's far exceeding that cutoff point of 30. So we can use the normal distribution, or you could use the t distribution. You're going to get pretty much exactly the same critical value either way, because as I mentioned, the t distribution approaches the z distribution when your degrees of freedom or sample size exceeds 30, and we're like far above that cutoff point. So what we're looking for in this critical value is we want 2.5% to be below the negative value of this critical value and 2.5% to be above the positive version of this critical value. So where is that in the z distribution? That's 1.96. How do I know that? It's something that you will memorize because you're often doing a 95% confidence interval, and when you assume normality and you use the z distribution, 1.96 is the number of standard deviations you are away from the mean to get 95% coverage. So it's just a common critical value that you'll use, and eventually you will memorize it as a result. You might also remember the empirical rule here, which is the 68, 95, 99.7. So, and that corresponds to the number of standard deviations away from the mean you have to be to cover that much area. So one standard deviation gets you 68%, two standard deviations gets you 95, and three gives you 99.7. And you might remember on your homework, a bunch of people were off by a rounding error, and that's because the empirical rule is a rough estimate. And you could see 1.96 is about two standard deviations, and it covers 95% of the standard normal. So, the 68, 95, 99.7 rule is rounded. It really should be like something like 67 point something, 94 point, or 95 point something, and so on. However, it's just a rule of thumb. But that should help you. I bring it up just because it should help you to remember that this 1.96 isn't totally arbitrary. It does line up pretty closely with what the empirical rule told us, which is about two standard deviations would cover 95%. And that's what we're getting about to 1.96. So you can use tables, software, or online tools to go from a distribution to the critical value. You just need to supply a few things. First, the probability associated that you want to be to the left or to the right if you want the positive value, which to be clear, you don't want to use 5%. You want to use alpha divided by 2 or 1 minus alpha divided by 2, which corresponds to 2.5% or 97.5%. Because we want 95% to be within our critical values bounds between the negative and the positive. So that means there's 2.5% on either side. So you're gonna specify whether it's left tail or right tail you're looking at. If you're looking at the left tail, you're gonna specify 2.5%. If you're looking at the right tail, you're gonna specify 97.5. Well, you could also specify 2.5%. And get the positive version. Or if you're looking at the left tail and you want the positive version, you specify 97.5%. So there's like a lot of ways you could type this in. But those are the two things you really need to specify is the probability below or above your critical value that you're looking for and the distribution's associated degrees of freedom if it's relevant. So for the T distribution, it will be. For the Z, there is no degrees of freedom. There's just one standard normal. And then if it's left-tailed or right-tailed, which corresponds to the probability that you supply. So that's how you would find the critical value using software or an online tool. In a table, it's the same idea. It just might take slightly longer to read and look through the table. And we already talked about why I can approximate with the Z. It's because my degrees of freedom and sample size is so large. And just to demonstrate, I'm going to go to R, which is the software I prefer to use. And I actually did this in R, I guess, in preparation for this lecture yesterday. So all software is a little different. In Excel, it uses inverse instead of Q. In R, they're going to use the prefix Q to do the inverse of the probability. If I wanted the probability, I'd do P. But I'm going to leave it at Q because I want the inverse, and I'm saying I want 0.025. Those are my degrees of freedom. And if I press tab here, it'll give me more arguments. So do I want the lower tail or the upper tail? I do want the lower tail. So by default, it's true. I don't need to specify that. Don't worry about non-centrality parameter and log P. We haven't covered that. And when I do that, I get 1.962175. So very close to what I would get if I did the same thing for the normal distribution, the standard normal, also known as the Z distribution. Let me just check real quick. That's all I have to specify because there is no degrees of freedom. And you can see the difference between the two is very small. So those are few ways to get your critical value, but as I mentioned, 1.96 is a really common one that you'll use all the time. Okay, so we go back to our formula now. We got the critical value 1.96, we got our point estimator, the sample mean, we got our standard error, which is the sample standard deviation divided by the square root of the sample size, and that corresponds to this confidence interval. You could also leave it in this form. This is valid. I would at least simplify the right-hand side, like this part, after the plus minus into a single number. You could leave it as 2.09 plus or minus whatever this evaluates to. You could write it like this with the normal parentheses because we want to include the lower and upper bound. Or you could write it in this format where I say my true parameter mu is at least greater than or equal to 2.005 or less than or equal to 2.175. All three of those convey the same information. It's really a matter of your choice how you want to write it. But regardless of how you write it, how do you interpret it? And I want you to take a minute to recall from a few slides ago how I asked you to interpret it. And then I'll go over it as well. So I would say like a semi-accurate interpretation is we're 95% confident that mu, our true population mean, is within this interval, however you want to write it. But the most accurate way to state it is we constructed this confidence interval with a process that if we were to repeat from start to finish, meaning sampling to calculating the interval, over and over and over again, 95% of these intervals would contain the true population mean. I know that's more verbose and not quite as clean as the earlier way to say it. However, it leaves less room for subjectivity and misinterpretation, such as that statement I said, which is not correct, which is that we're 95%, or there's a 95% chance that the true mean is in the interval. That just doesn't make sense, right? It's either in the interval or it's not. Again, this is a subtle semantic distinction but I think it's important that you understand the interpretation behind confidence intervals. All right, let's do another practice problem. So this time we're estimating a proportion, which we hadn't talked about, but I wanted to do this because some of your projects relate to proportions, and also because the standard error formula for proportion is something that I think you should know. So we're going to cover that now. So this is looking at how common allergies are. And so the Marist Institute surveyed 883 people. As soon as you see that, you should think, this is my sample size, 883. And ask them, are you allergic? And we got 318 people, or 36% were allergic. So let's calculate a 95% confidence interval for the proportion of people who have allergies in America. So remember our general formula. We have the point estimate plus or minus our critical value times the standard error. Our point estimate you should be able to see right away. Our standard error we have not covered for proportions, but it is also really intuitive. So go ahead, I'm going to flip back, take some time to think about that, and then I'll let you know. So our point estimate, there's two ways you could go about this. 318 isn't normalized, so I would not use 318, because if your sample size was different, the 318 would be different. So I think the better way to go about this is to use the percentage 36% for your point estimate. Now the standard error for proportion is different. We had that formula for standard deviation before. You don't even need a formula when you're dealing up with a proportion. Instead, what you do is P, or P hat, I should say, because it's the sample proportion. That's all hat means. Hat means it's my sample value, as opposed to P, which is my population parameter. So just like earlier on in this presentation, we talked about the distinction between X bar and mu, standard deviation and sigma. It would be the same thing here. It would be P hat on one side to P. P is the true parameter in the population. Hat, whenever you see a hat over a mathematical notation, is referring to what's happening in your sample. Sorry, I flipped too far. Okay, so you take your P hat and you multiply it by 1 minus the P hat. That's it. That's how you get your standard deviation. No subtracting the mean, no squaring, no summing. Very simple. You take what you calculated as, essentially, it's a mean of sorts, and you multiply it by 1 minus the mean. And that is the standard deviation of your proportion. And then just like before, that is the variance of your proportion, not a standard deviation. Your standard deviation would be the square root of that. And then just like before, you would divide by the square root of your sample size. So we have most of this done for us, right? We're taking the square root of 0.36 times 1 minus 0.36, dividing all of that by 883, all inside the square root, and plus or minus from 0.36. So we're just missing our critical value. So again, we'll do that. And you might remember from earlier that if our sample size is large, which it is in this case, 883, we can approximate it with the z distribution. And we know what corresponds to 95% in the z distribution is 1.96 is my critical value, right? So I take my critical value of 1.96, I multiply it by my standard error. That's my margin of error. This whole quantity here is my margin of error. And you have 3 different ways to write it again. You could leave it like this, although if you do, please simplify this. You could leave it in terms of the parentheses, or you could write it as P, my true proportion without the hat, is between 32.8% and 39.2%. Those are all valid ways to state your confidence interval. Yeah, so that's some practice building confidence intervals. As I mentioned before, this is the last topic we're going to cover before the optional material regression starts next week. Please start working on your projects if you haven't already. Reach out if you need any guidance. Schedule an office hours. We have 1 week of class before those are due, and I'm sure that there will be a lot of people scheduling office hours in that final week. So schedule yours early so you have more options and availability to choose from. and looking forward to see what you guys do for your final report.